Hello, this is Miss Rich, and we are working on our video for describing relationships. This is section 3.1 and 3.2, mostly from 3.2. And I want to go over some things that we touched on in class and continue a couple things as well. Let's get started. We talked in class about this first regression, this scatter plot. A regression line is a line that describes how a response variable y changes as an explanatory variable, which is x, changes. And here we had this data came from non-exercise activity, which meant activity. They were trying to see if people who were particularly fidgety or wiggled a lot, perhaps, and see if that affected the amount of fat that they gained over an 8-week period. So 16 healthy young adults were in the study, and they were fed an unusual amount of food over this time. And as you can see, we ended up with a negative relationship here, and we put in the line of best fit, and it's clearly has a negative slope. And we would describe the scatter plot as the plot shows a moderately strong negative linear relationship association between NEA, non-exercise activity, and fat gain with no outliers. So notice when we describe a scatter plot, we need to put strength. It's strong, moderately strong. We're looking at how spread the dots are from each other. What its direction is, meaning either negative or positive, and its form, which at this point is going to be linear or nonlinear. Later on, it could also be logarithmic, exponential, things like that. And so what this negative relationship actually means is, of course, as non-exercise activity increases, our fat gain is decreasing. And so that in context means, and know that that's in general. It is predicted. Not every value, if you go from this dot up here, for instance, from here to here, that's not necessarily changing the same way as it will be if you follow the line. So it's just in general what's happening as your non-exercise activity increases. Okay, we mentioned residuals. Residuals is our actual vertical deviation, vertical distance. The actual points, so these points are the actual points we got from our study, deviate from the predicted values, which would be the points that would fall on the line, from the prediction line, which is here, our regression line. A residual is calculated, the observed value, which is what we, again, get from our data, minus the predicted value. And the predicted value, that y hat value, is going to come by plugging into an x value. So, for instance, if you want to find this residual right here, the size of that residual, you would plug in that x value, which would be 136 or so, and for the x, and get your y hat, your predicted y, and then you would subtract it from what the actual y was, which is what you would get out of your data to get your residual. Positive residuals are, of course, above the line, and negative residuals are below the line. Always that vertical distance from the prediction. One of the first principles of data analysis is to look at the overall pattern and for striking departures from that pattern. A regression line describes the overall pattern of a linear relationship between two variables. We see the departures from this pattern by looking at the residuals. And this is where a residual plot comes in. If you take the plot and basically turn it horizontally like so, that gives you a residual plot. Residual plot is going to be the same x values here against the residuals, which we just discussed, are y minus y hat, each y value minus the actual minus the predicted. And so when we look at these residuals, we're looking at a couple of different things to tell if it's a good model. First of all, the residual plot should show no obvious pattern. If you look at these two residual plots here, they have these obvious curves, and they will be very obvious curves. And if that happens, you want to say, well, because of the curve in the residual plot, that there is probably a more appropriate model rather than a linear model. It doesn't necessarily talk about how strong the model is, the linear model is, but it does tell you that there's a more appropriate model. This is not the best model. Also, the other thing is your residual should be relatively small in size. Now, this is often a judgment call as to what is small in size. But what's meant by this, if you have a residual plot and you have points that start out pretty close to your residual line there and maybe fan out as you go, kind of like this, you'd want to talk about what that means in respect to the data. Here, this data down here, below this x value, is obviously much closer to the line. So the line would be a better prediction below this given x value than it would above it. So if you have a fanning out on your residual plot, you want to talk about that. The size of the residuals are getting larger as x gets larger in this particular one. Now, do you know that you will occasionally come across S in a computer printout generally, which are the standard deviation of the residuals, your little s. The standard deviation of residuals is very helpful because if you tried to find, well, approximately how far are the points from the line? Well, if you averaged all the residuals, then you would always get 0. You're averaging all these positive distances from the line with all these negative distances from the line. Of course, you would always get 0, so that wouldn't be any help. But the standard deviations of the residuals, which is essentially, so here's a residual, y minus y hat, square it to get rid of the negatives and positives, and essentially average them up, and then square root it again to get it back to out of the square, back to the same units as the residual. You can see that S would show you about how far off each point is from the line, which can be very helpful. Know that S is different from the standard deviation of X or the standard deviation of Y, which would be S sub X or S sub Y. Now, there's a lot you're going to see when you see a computer printout. Here is a mini-tab version. First of all, S right here is what we were just talking about, the standard deviation of the residuals. And it's predicted right here. It's how I would find a good way to predict it. This S, the standard deviation of the residuals, tells us that on average, the prediction error of fat gained from the model is 0.739. That's how far off the points are from the line on average. This value, r squared, is your coefficient of determination, which is interpreted right here. R squared tells us that 60.6% of the variability in fat gain is accounted for by the model with non-exercise activity. That's kind of the little sentence we're going to use to talk about R squared, and we discussed this in class. We'll see it again on the next slide. It's discussing that improvement by adding that X value in the variability. We'll look at that in a minute. As well, you can get your whole regression line right here, fat gain hat equals 3.505, so that's our y-intercept. Our y-intercept is going to be found right here, which is under coefficient, and next to constant, because it's the coefficient of the constant, which means it is the constant, minus 0.00344. That's our slope under coefficient, and next to the x value, NEA. And make sure when you write out this regression equation, you put it in context like we've done here. To interpret the slope of B, now remember, in regression, we call slope B and the y-intercept is generally A. The slope B equals negative 0.00344 tells us that the amount of fat gained is predicted to go down by that amount for each added calorie of NEA. So each 1 unit increase in X is how much is predicted to be changed for the Y. Make sure you include that predicted. That is key, because this isn't going to happen every time. That's just what the line is predicting that it'll happen on average. The y-intercept of 3.505 kilograms is the fat gained, so that's your y value, estimated by this model if NEA does not change. So y-intercept is going to be interpreted when X is 0, NEA is 0, then your y-intercept is 3.5. Your fat gain is 3.5. Now remember, this often won't be valid for the type of data you have, but here it does make sense, because if you're eating a lot of food and the NEA doesn't change, you still could be gaining weight, of course. Okay, other important equations for the least squared regression line is when you have to find the regression line and maybe you're not given slope and the y-intercept, maybe you're only given standard deviation of x and y, maybe you're only given r, which is correlation. This equation here is very commonly used. It's on your formula sheet. It's probably the formula that you will refer to most on your formula sheet that you'll actually use. And its slope equals the correlation r times the standard deviation of the y divided by the standard deviation of x. That's how you could find slope if you aren't given it. Now you'll use this a lot of times when you have a computer printout and they're not giving you slope, and but you still have the standard deviation of x, y. So remember, that's how they're going to be related. Also, you'll use this equation, which is confusing to look at first, but all it's saying is the point x bar y bar, which is the mean of the x's, the mean of the y's, is always going to be a point on your regression line. So if you have the slope and you have the and you're looking for the y-intercept, remember we call y-intercept A, you could plug in y bar, x bar if you have the mean of the x, y's, and you could find A to plug it back into your equation. It would be very useful. Okay, so here's a good example of where r squared comes from exactly. The coefficient of determination, remember what that's called. R is the correlation coefficient. R squared is the coefficient of determination. Is the fraction of the variation in the values of y that is accounted for by the least squared regression value of y on x. Now that sounds crazy. But all that means, if you look right here, SFE is the standard, is the sum of the sum of the squared errors, which just means the sum of the squared residuals. SST is the sum of the squared totals, which here y minus y bar, y minus the mean squared. Let me get rid of that. Oh no. R squared tells us how much better the least squared regression line does in predicting values of y than simply guessing the mean of y for each value in the data set. Consider this example was about body weight and whether or not it could predict backpack weight. And notice, if we didn't know people's body weight and all we had to predict it was right here, this line is the mean line, the mean of the backpacks, that would be the appropriate estimate if all we knew was a bunch of backpack weights. We would approximate anybody's just by using the average. So R squared is telling us how much better is it to use this line, this green least squared line, as the prediction instead. So if we look right here on this fathom, shows the sum of the squares. Here's our squares. And all the squared residuals. Look at that. If we sum up all these residuals here, we're getting the sum of the squares to be 83.8. So that's how all of our residuals squared and added up together. However, if we use the sum of the squares from the least squared line, instead we're at 30.9. The area of those squares is much smaller, so that variability has been improved. Our prediction, of course, is much more accurate using the least squared line instead of just the mean. So this comes in, our sum of our squared errors was that 30.97 value. Clear this. And our sum of our squared total was the 83.87, and that gives us this fraction right here. And if we divide it, we get 0.368, which means 36.8% of the variation in path weight is unaccounted for by the least squared regression line. So in other words, if we subtract that from 1 over here, that gives us our R squared. 63.2% of the variation in backpack weight is now accounted for by the linear model relating backpack weight to body weight. So in other words, this is now all that variation we can now account for by adding in that extra variable of body weight instead of just predicting it with the mean, which is very good. Of course, the larger your percent is, the larger your R squared, the better your prediction. Okay, a couple things about correlation, meaning R. Correlation and regression are powerful tools for describing the relationship between two variables. When you see these tools, be aware of their limitations. First thing, very common in multiple choices, is the explanatory and response. The distinction between the two is important in regression. But notice, look at these R's. Here's our R squared, 60.6, 60.6. If I change, here my X value is NEA, and here my Y value is NEA. If I switch those X and Y, our R values have not changed any. Some other things will change, but it does not affect correlation if you switch those X and Y values. Another thing that remember, the least squared line, slope, and the y-intercept, and R is only used to describe a linear relationship. It doesn't make sense to describe a curved relationship, for instance. R is talking about a linear relationship. And that's why, again, when you describe it, you talk about that strength, direction, and form, but the form will always be linear when you're talking about R. Note also the difference between your outliers and your influential points. Here an influential point at this child 18. Here an outlier at this child 19. And notice your lines are not resistant to those points, and your R is strongly affected. Here was our original R with all the data with negative 0.64, and here was our original least squared line. And notice, without that child 19, which was an outlier, our R is becoming stronger if we remove that one, and of course, because the points are now closer to the line. And the slope is changing, but only slightly. Removing that outlier, it has such a strong residual, it's not going to change the slope much. It's mostly going to change the correlation. Whereas the point here, if we remove child 18, look at the large effect it has on correlation. It becomes, if we remove that point, big change in the in our R value. It's a much weaker relationship, and as well as a very large change in the slope, because that point is an influential point. It's pulling that line towards the point and really affecting where the slope of the line would be. Last thing, remember, association does not imply causation. We also say a lot with this that correlation does not imply causation. We used the example in class about the amount of rum sold in New England states versus the amount of Protestant or Methodist ministers, and how that was such a strong, linear, perfect, almost slope of one, or R of one rather, between the two. But there was an extra variable there, and that was population. As population was increasing, the amount of ministers was increasing, and the amount of rum was increasing. It didn't necessarily mean as you were adding ministers, it was causing more rum to be purchased. So remember that the correlation or association does not mean that one is necessarily causing the other. They might just be related because of a different variable. Thank you.